my name is Garrett Warner. I'll be presenting this poster on the planetary boundary layer over heterogeneous surface heat fluxes. First, I'm going to go through our motivation of the research, our methodology, how we went about the research, and what results we found. We will go through our conclusions that these results gave us, and what future work we can look forward to. Our motivation for this research is that numeric weather prediction assumes homogeneity in the horizontal within its grid spacings, even though its grid spacings can be up to a few tens of kilometers. And in reality, the Earth is almost always heterogeneous regardless of the scales that are being used. So our objective is to understand the effects of heterogeneity on the boundary layer structures, specifically the effect of surface thermal heterogeneity. And how we thought this best was to use large eddy simulation. In this diagram here, you're able to see the domain used in this large eddy simulation. In the x direction, we defined the dimension as 8 kilometers, in the y direction 4 kilometers, and in the z direction 2 kilometers. In the top upper 500 meter vertical layer, we defined it as a sponge layer. This would dampen any vertical motion that was entering this layer so that the fluid would not interact with it in the top boundary, due to this being able to cause problems in large eddy simulation. We defined a geostrophic wind as 8 meters per second purely in the x direction. However, there is a Coriolis effect in this large eddy simulation, so the total wind will have a small v component to it. Since we want to find the effects of surface thermal heterogeneity, we defined 2 different types of simulations that we would run. First, a homogeneous surface heat flux simulation, where all the surface would have a surface heat flux of 0.05 Kelvin per meters per second. We also defined a heterogeneous surface heat flux simulation, where we divided the surface into 2 different patches. The first patch would encompass the first 4 kilometers of the x direction and the 4 kilometers of the y direction, and we defined this patch as 0 Kelvin per meters per second, which is neutral. And then we defined the second patch, so the second 4 kilometers of the x direction and then the 4 kilometers in the y direction, as 0.1 Kelvin meters per second. Comparing these 2 types of simulations will show us whether assuming horizontal homogeneity would be a okay assumption, or if the differences are too large and they would cause large inaccuracies in models. Our large eddy simulation uses the governing equations of the 3D Boussinesq approximation. The SGS model is Lagrangian scale-dependent dynamic Smirinski model, and our spatial discretization is pseudospectral in the horizontal and finite difference in the vertical. The pseudospectral causes our horizontal domain to be periodic, as we can see that in the end of this domain, it seems to lead right back into the beginning. First, we're going to look in our results section. We will look at the time development of the boundary layer height. In the x direction, we're able to see that it's boundary layer height. In the y direction, is boundary layer height. In the x direction is time measured in hours. There's 4 different lines on this figure, and the 2 of them are homogeneous simulations and 2 of them are heterogeneous, because we wanted to see whether homogeneous or heterogeneous had an effect on the boundary layer depth or boundary layer growth rate. But we also wanted to see whether starting the boundary layer at low or high heights would have any effect too. So each heterogeneous and each homogeneous simulation was ran for 2 different boundary layer heights, initial boundary layer heights, one for 855 meters and one at 140 meters. And what we're able to see is that whether the surface heat flux is heterogeneous or homogeneous doesn't really matter to the boundary layer depth growth rate. If we look at these 2 lines here, we're able to see that both of these simulations started at 1,140 meter boundary layer height, and we're able to see neither of these lines particularly grew any faster than the other, nor is the standard deviation very different. So we're able to see that that the growth of the domain average boundary layer depth is insensitive to heterogeneous heat fluxes considered here. And if we compare the two boundary layer heights, initial boundary layer heights, we're able to see the same, that these two simulations aren't growing any faster than these two simulations, nor are they any more turbulent or have a larger standard deviation than either one. So we're able to see that the growth rate of the domain average boundary layer depth is insensitive to initial boundary layer depth values considered here as well. However, if we look specifically at the boundary layer structure of the two heterogeneous simulations, we're able to see big differences. So both of these we plotted vertical velocity, heat flux, and wind speed gradient for the heterogeneous initial ZI 855 meter simulation and the heterogeneous initial ZI 1140 meter simulation. On the left, it's 855 meters, and on the right, it's 1140 meters. In each of these plots, we're able to see this black line. This represents the Y and time averaged boundary layer height. So we're able to see how it changes in the X direction and where the boundary layer height is going to be defined in each of these profiles and plots. And now comparing these two initial boundary layers, we're able to see that a lower initial boundary layer height has a very different vertical velocity plot than when compared to an initial higher boundary layer height. We're able to see in this higher initial boundary layer height that this updraft and downdraft is much more organized. We're able to see this updraft directly over where the surface heat flux changes, and we're able to see this clear downdraft right before it. However, when we look at this lower initial boundary layer plot, it's not quite as organized. We're able to see this downdraft directly over the heat flux patch change, and over the positive heat flux patch, we're able to see this downdraft for some reason, which is against what we would consider. We would think that over a positive heat flux patch, you would see a upward motion, a positive vertical velocity, but we, for some reason, do not. And we want to find out what causes these differences. And we know that vertical velocity is caused by surface heating and horizontal divergence. So to represent surface heating, we have this heat flux plots here. But what we're able to see is that the two don't really have any strong differences. They are pretty much the same. The only differences that we are able to really tell is that in the higher ZI simulation, that this thickness of positive heat flux is a little thicker. You can see that this yellow extends over this tick mark where it does not in this plot. So that's really the only difference, and that difference isn't really going to contribute to the huge differences we see in this vertical velocity plots here. But to represent horizontal divergence, we've plotted wind speed gradient in the x direction, so du dx. And this would represent horizontal divergence due to us assuming that v isn't really going to be changing very much in the v direction, since there's not really any forcing in that direction. And the largest thing we can see, or most prominent thing that we can see, is that in the lower ZI, there isn't any du dx above ZI, above this black line, which is expected. We don't expect to see any du dx in the free troposphere. However, when we move over to this higher ZI, initial ZI, we're able to see that there is a noticeable du dx above the ZI, which is unexpected and unconventional from what we would expect to be in the free troposphere. However, we're able to see how these positive and negative values of du dx correspond to these updrafts. That in this green, which is negative du dx, we're able to see updrafts in the same area in our vertical velocity. And the same in this plot, that this green and even some blue near the surface is causing this very strong updraft here. And the same for positive values of this du dx in these orange and yellow colors. That here we're able to see it kind of correlates to this downdraft right here, these positive values. And if we look over here, it's the same here. It's causing these downdrafts here. However, in these areas, there is no free troposphere du dx, so there is not really any explanation to why these higher vertical vertical velocity blobs are occurring. And over here, it's the opposite, that this positive du dx is aligning to this positive updraft in the upper layers, and vice versa for this green and blue area in these downdrafts. So in conclusions, going back to our first figure, we're able to see that the growth rate of domain average Zi is insensitive to heterogeneity in the surface heat flux and initial boundary layer values investigated. However, looking back at these plots, the heterogeneous surface heat flux simulations, when we separate them into two different initial Zi values, we're able to see that their heat fluxes are still very similar. There is no large discrepancy between the two. However, that we have completely different patterns in updrafts and downdrafts, and we have attributed that to the differences between our wind speed gradient du dx. And the largest difference between those two, which is unknown to us, is why there is this diverge or positive du dx and negative du dx in the free troposphere, which is going against our conventional understanding of what is occurring. But this opens up ideas for future work. We want to explore the cause of this noticeable du dx in the free atmosphere. And we would do this by conducting a sensitivity test with increased vertical domain size. So we will keep the boundary layer height, initial boundary layer heights the same. However, we will raise our vertical domain to be higher, because it could be that our sponge layer is affecting these results. Because as we mentioned earlier, our sponge layer begins at 1500 meters, where there is still some vertical velocity going on, and where most of this noticeable du dx above Zi is occurring. So we want to see if this is still occurring if we raise this sponge layer higher above the boundary layer, where it shouldn't really have any effect on any of these dynamics going on down here. But as well, to get some more data, we want to repeat this work with alternative surface heat fluxes and initial Zi's to see if we get the same things or anything different. For example, what if we have an initial Zi of 1,000? Does it look more like this? Does it look more like this? Or does it start to have its own pattern altogether, which would be very interesting. But really the end goal is to get a mechanistic understanding of the PBL structure. What key dimensionless numbers measure of the relative importance of horizontal divergence and buoyancy effects. That really concludes my presentation. I will take any questions whenever our poster session is available to you all. Thank you for listening, and I enjoy talking to you about this research.